So I hope you got recharged with coffee, cookies. There was fruit also. Now we are going to continue with the practical aspects of the method, what and how to model using the ISE and PPOA methodology. José Luis.
Okay, thank you, Carlos. The important question is, we have to model everything? No, we don't have money to model everything. We have time to model everything? No. So it's very important to identify the scope of what we need to model. And the methodology helps you to identify the scope. We are using all the diagrams of SysML? No. We have to be practical. Okay? Right now I am not academic. I am a person working in industry with an experience working in 6 companies. I am practical. You need things that industry, best practice that industry can apply. Okay? So, we are working in this area of DB, the definition of the system, using models. Next. So, very important, we use some engineering principles that allow us or guide us to select engineering best practices. Fault risk is an engineering best practice. And from this practice, we incorporate this practice in a process and steps that we call that a methodology. So engineering principles drive best practices that we use in different steps of the method to model the system using views. These views are represented with a notation that is SysML or another thing. Another artifact we recommend is the N-square chart that is not supported by SysML, but is very helpful from the engineering point of view because it's a representation, a schematic representation of interfaces. The N-square chart is very helpful. It's an old best practice. It's from the 70s of the 20th century, but it's good. It's a good engineering practice, and we implement it in the modeling tool. So, for us as engineers, it's important the scope of the model, what we want to represent in the model, and the fidelity, the detail of the modeling. You have to play with the both scope and fidelity, but don't sacrifice scope, sacrifice fidelity. Okay? So the principles driving this methodology are breadth first development. The important issue is first, identify the subsystems. ¿Puedo usar esta? Sí. You have a system. A system is for you a black box. The system interacts with the universe with a context in the universe. This may be persons or other systems or the environment. There are interactions. Okay? For example, this one is the environment. And this one is the pilot, for example. Okay? These interactions, you model these interactions as interfaces. And you go inside the system. And you have subsystems. Okay? So we call this approach out-in. Very important. Go from outside the system to inside the system. To the contrary, as the engineers and the universities work. That is, going from inside, the tile design, to the outside. It's the contrary. From outside to inside is another way of thinking, system thinking. Outside, inside. Not technology-oriented, function-oriented. In the universities, you are technology-oriented, and your professors teach you technology, and you are very happy with technology. But technology changes. Functionality doesn't change. Technology changes. So very important for us, functionality. Form follows function. The physical design is based on the functional architecture. This is a principle of buildings invented by an architect, Sullivan. Sullivan was an architect in the University of Harvard. Sullivan teach, another architect very important is Wright. Form follows function. You design a building based on the functionality of the building, not to the contrary. Engineers identify the functions of the thing and after design the thing. Not design just a technology for everything. No, it's not the way. I remember always when I worked in a phone company, mobile phone company, and one of the problems was that the phones were not designed for older people. The phones were think by engineers, young engineers, and older people is not important, and it's important because in Europe, older people is a broad part of the people in Europe. So we need phones adapted to older people with buttons, large buttons, less functionality, whatever. Out-in approach. If the phone is to be used by an older people, adapt the phone, the design of the phone, the functionality and the design to these people. Okay? So these are the principles, the basic principles. Next. So, scope. The scope is, so in this out-in approach, you define the scope. All inputs and outputs should be considered. Second, use cases. If there are interactions between one actor, the other person, and the phone, you need to model these interactions, use cases. You need to identify all high-level functions of your system. It's the most difficult thing, because you are not used to work in the abstract world. You are used to work in the detailed design world. For you, the most difficult, in my experience as professor, identify the functions of a thing. For example, identify the functions of a washing machine. Washing machine.
Yes,
Washing machine, not a function. Washing is the goal. The function, for example, is extract dirt. You have to think more in the level of transformation. The goal is wash. The function is remove clothes, extract dirt, etc. And this function can be implemented with different technologies. Water, or in some cases, you can extract the dirt of a cloth with ultrasounds. It's another technology for the same functionality. As engineer, think in functionality, not think in technology. All quality attributes. For you, it's important in this project usability, safety. You have to think the qualities, attributes you are important for you. Not all. If you have a customer says, all the quality attributes are important, it's stupid. No, you have to think what quality attributes are important for you. In your project, what quality attributes are important? for example? An autonomous robot. Safety. Robustness. Is usability and qualitative important? Not always. It depends on the level of autonomy. Resilience? Yes. There is a qualitative that is called resilience, and there is a quality subfactor that is called man in the loop. When you have an autonomous system, the person that is near the autonomous system has to know the state of the autonomous system. That is called man in the loop. So it's important to identify the quality attributes and model it. Here we are writing the diagram or the modeling artifact we recommend. All subsystems and the interfaces. All subsystems and the interfaces. Okay? And also the interfaces of two systems with the output, with the context. Okay? Interfaces in systems engineering are very important. And requirements. This is the scope. We recommend to use this scope. Don't sacrifice the scope. Sacrifice the detail level in these models. But don't sacrifice the scope. Okay? But more or less this was explained by Carlos. So very important, out-in approach. How the system operates in a context. Identify the needs of these people using the system. People or other systems. After, identify external interfaces. Identify the functionalities of the system. Specify requirements based on the functionalities and quality attributes. Identify subsystems and their interfaces. So this is the approach. From out, in. It is easy to apply? No, but it's good. When you apply the method, you feel good. Because you see that the models are consistent. The diagrams are consistent with this approach. Okay? So we have these diagrams are grouped in three dimensions. The mission dimension related to how the system interacts with the external world. The system dimension inside the system, and the software dimension if you have software parts. So you have three dimensions. External, mission. Internal, system. Software intensive, software. You have to work with deliverables in the three dimensions. And the important thing is that these deliverables in the tool, if you work with this approach, are consistent, are integrate. These deliverables are, the model is unique. These deliverables are use of the model. Think in a hypercube. You have a hypercube, a polyeder, and you have different faces. The views are the different faces, but the model is unique. So, in the first part of the methodology, we work with the mission. So we identify scenarios. In the case, for example, of medical device, the actor is medical device inside the body, a surgeon. Surgeon operates with this device. The surgeon has different scenarios when the surgeon is interacting with the patient and the device. Here is the surgeon, here is the patient, here is the environment, here is the device. You have scenarios. You have to model scenarios using use cases and also using misuse cases. For scenarios related with safety and unintended behaviors, you need to use what we call misuse cases. In some cases, the actor in misuse case is bad luck. It's an incredible actor, bad luck. So you need to model intended behaviors and unintended behaviors. Important. You understand me? You follow me? Okay. So
We go now to a
Carlos will explain.
practical example. So I have some examples of the process for an underwater robot. These are some simplification I did for today based on the excellent work that Gustavo is doing on modeling the AUVs that we are building, coding, programming in the project. So an example for the AUV of the context diagram that José Luis was explaining with the stakeholder and the system, the different subsystems. So in our case, the system of interest is the AUV, right? We probably have one operator. Probably the AUV is going to connect to some kind of base where it can recharge. Please, if anyone says, yeah, you should use this other name, please tell us, because then we will adapt. We are experts on systems engineering, not on AUVs yet. So I very much welcome your comments. The AUV is interacting with an environment. Probably we could specify this a bit more because this is just vague, but we have more specifics for underwater environments. And an element of the environment that we have separated because it's so important for the case, the exemplary case that I will be using, is the pipeline. So this AUV is inspecting a pipeline. So being that important, it makes sense to show that in the context diagram as a separate entity here. As José Luis mentioned, we describe the intended behavior of the system using use cases and scenarios. So we use templates with preconditions, post-conditions, triggering events to specify each scenario. So potential scenarios for our case can be grouped into deployment of the system, so we don't forget that we actually need to put this in the water and there might be some operations needed for that, and operation. So a couple of potential scenarios are system configuration and calibration. This is a standard for any robotic system and many other systems. Probably the first thing after calibrating is actually mapping the environment. So if the robot is supposed to be inspecting the same infrastructure over longer periods of time, maybe the first thing that needs to happen is that we get a map of that environment to use during the regular operation. For example, using the SLAM techniques that Michael was explaining yesterday. And then we go into operation phase. So what do we want our robot to do? Inspect the pipeline. So this is probably the main scenario. But we have other scenarios, as José Luis was mentioning, that are maybe not that intended, but we know that they will happen. So we need to model what we expect the system to do in the case of an emergency stop, for example, when something goes wrong. This is not the same, we don't expect the same kind of things to happen in a robot on the ground than in a robot underwater. So in the case of an underwater robot, maybe we want the robot to surface in a safe way so that we can retrieve it and not to stay down there. So maybe we don't need to stop, or we don't want it to stop all functionality. Maybe the search functionality needs to be still active to be able to retrieve the AUV. Again, please raise your hand and say, hey, what you are saying doesn't make sense. We actually do this because you know better. Another scenario, maybe during the operation, not all the time, the robot needs to actually communicate and download the data it has retrieved in the base station, for example. I'm not sure. I don't know if anyone has a concrete idea of how this should work in the example that we are working in REMARO, please let me and Gustavo know, and we will model it properly. So this was just an example of, yeah, hard.
So in this model, you have very specifically modeled pipeline. So I think that's not a abstract model. So if the scenario changes, you cannot reuse this model, or
That's a very good point affecting reusability. So we are modeling a system that is used for a purpose. So in this case, that system is inspecting pipelines. And that's a very valid point. So if I start modeling this, how does this affect my design? So here, this is a context diagram, meaning that this is an external entity to our system of interest. So we are making sure that we will capture the requirements needed for the pipeline inspection. But when we do the functional architecture, it's our role, if we have some reusability requirements, to make sure that what we are doing here complies, is able to inspect the pipeline, but it's reusable for all other cases. So there would be additional constraints in our design during the functional architecting if we want to do so. The nice thing about doing it following the function is that we separate which functions correspond to the pipeline. And that ensures that our design will be reusable because we can just take out that part for the next AUV, but the rest of the subsystems that are allocated for other functionality are still there. So we can reuse our functional design. That's why it's so important to separate your functional architecture from your physical architecture. Because if you start embedding in your decision of the components the things related to the pipeline, you will not be able to reuse your design. But if you have traced those requirements to concrete functions, then you can safely reuse the rest. That's a very good point about reusability. Mm-hmm. But, yeah.
Okay. When you identify the scenarios, you have to identify high-level functionality, high-level functional requirements, and capabilities. Capabilities is a very complex concept, most used in two areas, military and space. And the definition of the military and the definition of NASA of capability is not exactly the same. NASA, for example, relates capability to technology. For example, you have capability of nuclear propulsion, you have nuclear propulsion technology, you can go to Mars in less months. So you adapt your mission to a new capability, that is nuclear propulsion. In the case of the military, it's more related with that. Is a capability is the ability to perform something. Capability is the ability to perform something. So the military study the mission, and in the mission, they identify gaps in capabilities. These gaps in capabilities is you don't have the capability to destroy the enemy. Okay? Because you have capabilities and the enemy has capabilities. And you see if your capabilities are enough to destroy the capabilities of the enemy. And you identify gaps in the mission. Capabilities, ability to perform something. Okay? And the capabilities group, properties. Properties that are quality attributes, physical properties, functional requirements.
So we have a quick example. So to identify the capabilities of a system, you can also reuse the domain of the knowledge, right? So there are already experts on what an underwater robot should do. So very concretely, you can just go to REMARO website and find the expert in the project, including our system engineer right now, Gustavo, who is gathering all that by reading all that, what these people are writing, right? So this indicates that this is just two little pieces of the document some of you have about, that I don't know how many pages it is. It's like 30, 40 pages already, and it's still on an infant base. But he already identified all these capabilities for our pipeline inspection robot, right? So, and just to give a concrete example, so it should be able to inspect pipeline, but it needs to be able to localize the pipeline. It needs to be able to navigate through waypoints that we give to it. It should be able to classify faults. It should have situational awareness. Hopefully also self-adaptation capabilities that we will discuss later this afternoon, and so on. I'm going to just, José Luis already mentioned that at this stage, we will also specify the quality attributes, and he has already discussed about the ones that you want to focus on. We need to speed up, so I'm going to jump into the example. So it's very important to first transform the needs into system requirements and not go too early into specifying very detailed component-related requirements. So first, you identify your system requirements. So for example, this is one requirement. The onboard camera shall work within a temperature range of minus 10, 30 degrees. Why do we have a camera? Why are we specifying this now? Basically, we are still at the point of identifying what the system should do, the functionalities, right? So this is not the moment in which we specify the range of temperatures for the camera. This is the moment in which, if we are interested in reliability in our system, we start specifying, for example, what is the mean time of, that the robot needs to be able to operate without human intervention. This we can specify now, because we are discussing what we were discussing, the needs of the stakeholders. So we have our system, the operator. We can specify what's the relationship between both, but not go into specifying now about the camera. Okay. So just an example of don't try to specify low-level requirements too early, or you will mess up with your reusability of your design. So the capabilities, I continue with this one to speed up a bit. So you identify the top-level functions of the system, which are closely related to the capabilities. So you can simulate both. So the output is the top-level part of the functional architecture. So the basic capabilities or high-level function that the system needs to be able to perform. Here we are talking only functional stuff, not quality attributes. And this is something that the systems engineers perform with the customers and users, so all the stakeholders. Concrete example. So to identify the high-level functions, again, we can take a concrete example of what people do in this domain. So this is actually a paper that Bas van Vliet from Lobster, and doing a master graduation project with me, found on what functions does an underwater robot need for docking. So some people already wrote about this. They already identified different systems, guidance, control, navigation. So probably our high-level functions should represent those, right? So we can have the localized pipeline. That's very specific function for our case, but follow the pipeline. That probably relates to this guidance subsystem. So this means that you can use the domain models, what other people already know about your domain, to identify your high-level functions. Okay? Environment awareness, that relates a lot to navigation. They already identified situation awareness to identify what's around the robot, for example. And you have the control subsystem, so a function to control the motion of the AUV should also probably be there. Yes, hi.
So 4 sounds like it's sort of out of place. It doesn't sound like a function to me. It sounds more like a property or a quality, right?
For which one?
F4, environment awareness.
Yeah.
To be aware of your environment is more, obviously you need functionality for that, but the other ones are all active verbs, like localizing.
That's a very good point. That's a very good point. That's a bad formulation of a function or a functional requirement.
Okay.
It should be expressed active with a verb, not with a noun.
So what would be effective? I mean, you could cheat as it being aware of the environment, but it doesn't sound like
Depends on how you do it, but it can be update your environment model, update environmental information, perceive environment. At this level, it can be quite abstract. Later, it will refine. But that's a very good point. We identify verbs here, what needs to be done. That's the difference. Here, they are talking about subsystems. Here, we are talking about functions. Functions are active. Those are verbs. Very good point. Thank you for the typo. Decompose function into child subfunctions. So now is where we start architecting the system, dividing those high-level functions into, okay, so to update the information about the environment, what does this mean? Do we have different inputs and outputs expected from this function? There are sub-functions that can perform those independent transformations, for example. So we are aware of the environment means that the robot needs to know what is the current pressure. Does that relate to knowing where the pipeline is? Maybe there are two sub-functions generating different outputs. And again, we go from the out-in perspective. So out, what are the inputs to the system? What are the expected outputs? If they are different, if there are multiple that are not related, maybe we have separate sub-functions for that bigger function. So we start decomposing, basically, from the first level of functions into different subfunctions. And this is where the method starts helping on making those decisions to what level of granularity. And the important thing here is we complete one level first, and then we move into the next one.
Only a point. The level of granularity, what do you think is the best level of granularity? What is the criteria to know that the tree is enough depth? I want you to think. What is the criteria to know if the functional hierarchy is enough? The criteria is allocation. You need children level functions that can be allocated independently to different parts or different subsystems in this case. If you have a function that is in every place, this function is very complex. Split it into children. You understand me?
Outsourcing? So when you can outsource the
Yes, yes,
design?
yes. So split functionality until you have the level of functionality that can be allocated independently to different parts. Parts that may be complex parts or simple parts. Allocation is the criteria, okay?
Yes, so this, they can trace it back to the allocation.
Can I ask a funny one?
Yes?
What if you have a function that is not easy to split because it
Correct.
let's say something like logging?
Perfect.
Yeah.
There are functions that you can allocate to different parts. For example, a typical function that is not split is head transfer.
Okay.
Head transfer is in every part. If you have a car, you need to transfer heat in every part of your car.
So would that become like a sub-function to main trees?
Correct.
So the trees are basically graphs then, because you can reuse. Okay.
But the trees are very important. In the physical world, engineers, how they call engineers the tree in the physical world?
Feature diagram? Feature diagram?
No, in the physical world.
Ah.
Feature diagram is more similar to functional. The bill of materials, engineering bill of materials. There are different bill of materials. Engineering bill of materials is more related. Pon el otro, Carlos, uno que ponía jerarquías. Esto. This one is in the engineering bill of materials. Subsystems, parts. There are other bill of materials that is called manufacturing bill of materials. So you have different trees, different bills of materials that industry use to develop a product.
We really need to speed up. My suggestion would be we skip the requirements part. So we are going slightly fast because we are out of time. So we already discussed a bit decomposing the functional architecture and the relation to allocation. That already relates to the physical architecture, meaning the decomposition of the system on the physical side, on subsystems, components. When I say physical, it's not necessarily hardware. It can also be software. So it's logical components of the system. We will see with a practical example how we start representing the functional architecture. So we already saw how you can represent the functions as this hierarchy. This is a UML class diagram, aggregation, composition. We will discuss a bit about the n-square, these nice metrics that allows to represent the interfaces in between functions, and we have already discussed functional diagrams. So José Luis just discussed a bit about allocation, so I'm going to skip this part for the sake of the example. Again, first the scope, afterwards fidelity. So you complete one level And thanks to allocation, you start defining the next level, decomposing the functions, and you repeat. So typically what happens is that you decompose one level of functions, you start allocating to subsystems. There are quality attributes that you cannot allocate, but define the design of these subsystems. And once you have those, this definition becomes the requirements for the next level, basically. So this is also a scope out-in, and iteratively you go down the hierarchy. This is an example of the modular architecture of the AUB, the subsystems, but I think the most interesting thing is just to jump. So we are not covering today, but you can check some papers and in our book how design heuristics are what allows you to implement quality attributes, basically. So safety, reliability, you don't allocate, you implement using heuristics, architectural patterns. We have an entire module on requirements, but I think we are going to just jump. So you can read this on the slides. José Luis already introduced a lot before about the requirements and the relevance of it. So there are some practical tips here on how you can write requirements.
We are offering some requirements boilerplates. You don't invent requirements from scratch. You have templates, depending of, for example, for safety, you have templates that you can fill with your requirements. Okay, for example, here you have a template for a functional requirement. When condition, the functional requirement really is the output of the function. Okay, every output has to be specified as a functional requirement. Okay, every output of a function should be specified as a functional requirement. This is the criteria. And using template. Okay, if you write some quantity, is what we call a functional requirement plus quantity, performance requirement. Functional requirement plus quantity, for example, this function should be activated each 5 seconds. Performance requirement. Okay?
You have all the slides on a PDF I sent this morning. Yeah.
So far we talked about the top-down approach for defining the requirements. Do you have, maybe it's in the next slide, I'm just jumping ahead, but is there anything bottom-up approach?
Correct. The flow down. Yes. Requirement flow down. It's a very difficult issue. For example, the chief engineer of the Boeing 787, one of the most difficult topics they have to deal was requirements flow down. But the trick is in the case of functional architecture, you have this trick, this best practice. You build the functional hierarchy. Okay? At each level, the requirement is, the functional requirement is the output of the function. If the function has 2 outputs, how many requirements? 2. So at E level, if you have 1 output, the requirement is related with O3. Okay? Next level, you have more requirements. Requirements are the outputs. If you have here 2 outputs, you have 2 requirements. You have here 3 outputs, 3 requirements. Okay? This is the rule. So at each level, so the flow down, you work in this. You work. Here you have top-level requirements, and when you split F1 into functions, you have more. Here, for example, you have one requirement, and here you have 3 new requirements that are children of this requirement.
José Luis, this relates to the requirements flow down. So that's the top down. And Sasan, you were asking for if there is any bottom up. And actually the answer is yes.
Yes, in some cases.
So when I mentioned before that you can identify the high level functions from existing models of the domain, right? But there is another way. So if you don't know, actually, there is no previous experience for that system, what you have is, how do I want my system to operate? So the description of the scenario, you can model, for example, using an activity diagram. And you go from the very bottom, like, I want this to happen, this action to happen, and this one, and this one. And you end up with a gigantic flow diagram. And then you start thinking how you can group those. What actions make sense jointly in a system. And you start aggregating those, and that's the bottom up. And we are actually going to see quickly an example later with the software architecture, because we actually did that way for the pick-and-place robot.
Correct.
We defined the functional flow in atomic actions, and then we started aggregating functions, and that's the bottom-up approach for creating the functional architecture.
But you have to have some criteria to aggregate steps in a father and parent function. What is the criteria? The inputs of the children and the outputs should be the same inputs and outputs of the father. This is the criteria.
And one tool to do this that I will quickly mention is this n-square chart, this matrix of interfaces, because that allows you to model the interfaces in between functions, inputs and outputs, in a mathematical way, where you can apply methods of clustering. So sorry for the weird setup, but if we want to record this, I need to put it in the main screen. That's why I'm switching all the time, just to put the blackboard so that also gets recorded. So we are going to be discussing the functional architecture. We have already discussed a lot, so I'm going to just go quickly. We are going to be focusing on this part, right? So this is where we identify, we decompose, we represent. It's actually quite mixed with the allocation, because it's an iterative process. So even if we are going to be focusing on that part, it's mixed with allocation, but we are not going to enter into the details of allocating, especially the heuristic part. José Luis already mentioned the idea of a function as a transformation with a nice example of the washing machine, right? What is to wash? You need to really model that as a transformation. So you want to have dirty clothes entering, and you want clean clothes plus dirt separate, for example. So you need to think of the transformation that needs to happen. And those can be matter, energy, or data transformation. And in the systems we are talking about, it's mostly data. But we shall not forget that there is an underwater robot in which there are also mass and energy exchanges and functions. That's actually happening in the physical world. So are there mass transformations? Well, actually, there is motion, right? So the robot is moving from one position to another. So there are actually a transformation, physical transformation happening there.
For example, if you have, an electrical motor, what is the input? Here is the motor, the function of the motor. What is the input? Electricity. And the output? Torque. So every function is a transformation from an input to an output, produce torque. You need energy to produce torque. And the function produce torque is allocated to a solution, an electric motor.
We have already discussed how important it is, because the functional architecture is independent of the technology, so I'm not going to go through this. How it relates to the V model. Let's just go to the practical example and do one thing. We are going to do 10-15 minutes, and then we do one break before the invited lecture at 12:30. Okay? So we are going to go quickly but focusing on the example. So there are three things that we need to do in the process of decomposing the functional architecture of the system. So we decompose it, and meanwhile we identify the interfaces, so inputs and outputs from one function to the other, and we create the functional flows. So which functions happen in which order, basically, in the system. So these are the three aspects that we need to take into account. We are going back to this example, the collaborative robot, and here is the top-down versus bottom-up approach. So I show you for the AUV how you can just look in the literature what are the functions that your system is supposed to have for that domain. If you don't know, you can write down, try to model in an activity diagram the expected operation of your robot. And that actually, this is the diagram I draw first when creating the functional architecture of the collaborative robot. And then I started to figure out, hey, all this is kind of the motion control subsystem. All this is actually to detect the obstacles, for example. And you can actually merge both approaches. So you expect to have some high-level capabilities or skills in robotics, right? So you can start figuring out, hey, all these actions that I'm doing, they correspond to what people talk about when they talk about SLAM, for example. So you start identifying that can help you also group cluster your actions. So with that, you end up having this decomposition at the first two levels, basically. So we need to handle the interface. In this case, usability was important. There is someone there interacting with the robot to produce an order. The system needs to be able to manage an order. It needs to understand that, hey, you are asking me about for this, and this product, so I need to decompose this request into which kind of motions do I need to do to pick them up, for example. And that's separate from controlling or planning those motions. First, you need to figure out what actions the robot needs to do. The actions need to be coordinated. That's something that is not represented in activity diagrams or in flow diagrams. You show the flow, but there is someone responsible for coordinating that flow that is implicit or abstract in that diagram. So this is important to take into account, especially in the case of autonomous robots. So I'm not going to go through all of them, but you can figure out all the steps that needs to happen, different functions here. So I'm going to explain the functional interfaces. And this is the n-square matrix that we have been discussing. So basically, you represent in the diagonal the functions in one level. You represent in the top row the external inputs to each function. And on the rightmost column, the outputs to the exterior of those functions. Right? And in each cell, you represent the output and input, the output from B that goes into C. So columns are inputs, rows are outputs. And you model it this way. So in the case of our robot, we have that there is a product request, and the function manage stack of products is actually obtaining, A, from what I know, this type of products I need to pick from this box. That's what we call the product index. There is, so that's isolated information, which product needs to be picked now. But there is actually the controlling, like we are now picking this one. So request the pick. That's also coming from the outside. So this is actually representing only part of the control subsystem. So you do this matrix at different levels of your system, okay? So for example, basically, after deciding this, there is the function to obtain grasp trajectories, but to grasp, you need to know that you are already in the grasp mode, and that's something that the function to move tells this other function, basically. So you identify these inputs and outputs. This one is only responsible for generating trajectories, but there is another function that is actually executing the trajectories and picking that. But to do that and successfully pick the product, it needs to have suction activated. So there's another function generating that output.
Only one comment here. This matrix is very helpful because if you build this matrix and all the cells are blank, you have a problem. these functions have no relation between them. So that if you have this matrix, you have that this function, inputs in columns is the criteria. This is an input to this. The output is, for this is an output, okay? Another very useful thing, below the diagonal, with this criteria, input is in columns, what is below the diagram? There is nothing. If there is something, what is? Below the diagonal. For example, if something here is an input to gripper, to activate gripper from execute motion. It's a feedback. Below the diagonal are the feedbacks, very important. And if two functions are very... Yes, continue with that, Carlos.
Oh, yeah. So
No,
exactly,
no.
José Luis was already pointing to the benefits of this representation, and is that you can identify all these patterns for interfaces. For example, the feedback that José Luis was mentioning in between two functions, that they have an input from one and back to the first one. So you can identify feedback loops, but you can also identify potential clusters of functions because they are highly connected with inputs and outputs here. So you expect this matrix to be close to a diagonal matrix if it's nicely defined, basically. So there are not connections in between all elements. So if you architect it properly, reusably, then it should look like a diagonal matrix. And actually, the people developing a method called the design structure matrix, which is basically an n-square matrix at MIT, they develop clustering algorithms to actually start reordering the elements in the diagonal so that you make the matrix diagonal, so as many zeros as possible around, so that you have a more modular design because the components have less interfaces, you have less connections in between elements, which is desirable for reusability. Yes, Harsh.
How do you specify parallel functions? Because we have a functionality that we want to move the object from A to B while making sure that there is no...
And that's why there is not an automated version of this yet. And especially in autonomous systems, I will show you with example, this is very, very complex, especially with the systems we are developing because there is a lot of parallelism. So this works very nicely with process-like systems that are processing from one input to one output.
Basically pipeline architecture, right?
Yeah, exactly, pipeline architecture. So
Autonomous systems are very rarely pipeline architecture.
exactly. So that was actually the conclusion of the example I was going to challenge you with, but we are running out of time, and you just jump to there. So this is all very nice, and it's actually very important to do, but there is still big challenges applying this, especially in our domain. And that's why we are still doing projects, research project on that, right? Because it's still a craft, an art to architect all this. So you can apply methods to some extent, kind of blindly or apply. But without the engineer thinking, we haven't solved this design yet, basically. Hopefully, with the methods that we are developing, we will end up with something a bit more automatic. I think we have already discussed this.
Very important.
This is very important. So to model the flow of the in-between functions, there are some rules regarding how the tokens work. And if you want to model a sequence, that's clear. If you want to select between two functions, you use a decision node and a joint node. If you want to iterate, you need to also add this merge node here. You cannot just put this directly in here because you will end up with some undefined behavior depending on the token flowing, right? And when you want to model concurrency, then you have the fork and merge nodes. So this is some notation to clarify the semantics
It's
of the flow.
important. Consider, Carlos, that these arrows are flow of control, not the flow of items. Okay? This is the flow of control. So when this function finishes, it activates the next function. This is the flow of control. Think in tokens, in Petri nets, okay? Similar. So this is typical constructs we use as engineers to build what we call in systems engineering functional flows block diagrams. In traditional system engineering, we use a concept that is functional flow block diagram. This is typical constructions we use, okay?
So we reached a bit late our practical example. So what I'm going to do is just present you with the problem, and then you can have some thinking about it, and then we will take some 5 minutes at the beginning of our next session about the software architecture to discuss the one possible solution. But let me guide you through the exercise. So this is what a system architect is faced with. So you have your description of your AUV system. This is the one from REMARO, conceptually, thanks to Jeremy. We already have a visual of that. It's not built yet, but will be, maybe. So we have our context diagram. We have something that I will mention, what the system is changing, and that you can just model as a list of items that are changed with environment. We have, let's assume, in a previous step, we already identified the high-level functions, and we also created our n-squared chart. So this is our givens. So the description of the system, the underwater vehicle is used to autonomously inspect oil pipelines that are located on the seabed. The inspection goal is to detect and classify faults in the pipeline component. So along the pipeline, there might be cracks, surface damage, warping, leaks, etc. So the AUV must be able to autonomously find and follow and inspect the pipeline. So far, so clear? So this was the context diagram for our entire AUV. So it's interacting with the operator, with the base, with the pipeline, and with the environment. But we are going to be focusing only in the control system, the software part. That's what REMARO, our project, is focused on. So this is the context diagram for that subsystem. And it looks, of course, especially similar to the physical architecture of the entire system becomes the context for this subsystem. So this entire thing is our AUV, simplified version of it. We have the operator interface, we have two sensors, sonar, camera, we have the propulsion system, and we have a database where we are creating this map of the pipeline, the environment, and annotating the faults that we identify.
Carlos, only one comment. When you build this new context diagram, the other subsystems are the new actors. You understand? The contexts have changed. When you have a subsystem as the main part, the other subsystems are the new actors, and also actors from the environment. This is the reason that here appear subsystems that interact with my subsystem. Okay?
So next to that, we also have what is being changed. So we have the image that is coming to our control system. We have basically the readings of the sensors. We have other elements that are actually internal. So I made a typo here. It was meant to be a discussion. But don't worry. This is the things you can play with. And those you identify in the n-squared matrix. So those are the inputs and outputs for the n-squared matrix. So if we move, so we have the functions, right, that we are going to put in the n-squared matrix. So our system needs to be able to manage, coordinate its mission. And that's a function that sometimes we forget. So I've put it F0 because I actually forgot at the beginning. And when I was drawing the functional diagram, I was missing something. And then I realized I forgot my manage mission or coordinate mission function. This is something that you can just reuse from designs, basically. So I reused from my previous design for a collaborative robot. Function to localize the pipeline, to guide the AUV, localize the AUV, the methods that we learned yesterday afternoon, etc. So this is our matrix and peak. So mission command, function to manage mission, generates what is the target pipeline. Maybe there are multiple in our environment. It can be a complex. So we identify which one do we want to inspect now. localized pipeline function indicates when that's done, then the guide AUV is responsible for following the pipeline. So for that, it generates a trajectory that is used by the control function to actually generate the thrust commands, basically. Not propulsion yet, because this is software. So the thrust command gets converted into actual thrust, basically, by the hardware of the system, and eventually into motion of the robot. But that's out of the scope of the control part of the system. So here is all data. Input and output are data, not energy or matter. For that, the body parts of the system, the hardware is responsible for. So you can see that the localized AUV generates the AUV state estimation techniques from yesterday. Monitor environment is generating obstacle information that is may be also used to drive the motions. So if there is any close obstacle detected, that might go directly into the local motions of the robot to avoid those. And actually, if you, depending on how you have your state estimation, you may use also the current control command to estimate your state. So here you can see actually a loop in between localized AUV and control AUV. So the exercise is to, okay, so now with this input, now we want to create our flow diagram. And so I'm gonna let this here so that you can think about it. There's a lot of parallelism here that you cannot, this not actually capture in the n-square matrix. So this is way more difficult than it looks or that it was in the collaborative robot, in which is a sequential operation, basically. So it's a bit tricky. But I will leave you to think about it. And later we will spend a couple of minutes discussing the solution. So I can give you a glimpse. Yeah, you got it? So let's just...
It is not easy.
This is the discussion of it. And so later we will go back to this after the break. I think you need a 5 minutes break. We are going to have a more research related talk, and then we have lunch. Thank you very much. I'm sorry for running into your break.